Hi everyone. After talking about the basics of game theory and the concept of Nash equilibrium, in this lecture we are going to go over game theory applications. So we're going to go through different types of games, in particular in economics, and see how to solve for the Nash equilibrium every time. First, a disclaimer. I do not allow this content to be published without my consent. If I see it uploaded online, I will take it down and report whoever uploaded it. So, many models use the notion of a Nash equilibrium to study economic, political, or biological phenomena. Often these games involve continuous actions, not just strategy A or strategy B, but sometimes actions and strategies are continuous. For instance, choosing a price, choosing a quantity. You can always include as many decimals as you want, and this gives you an infinite amount of possible actions. In particular, in this lecture, we're going to see how to find a Nash equilibrium in these cases. So, a couple of examples. Firms choosing a business strategy in an imperfectly competitive market. So, firms one way or another have some form of market power. It could be due to different reasons. Because of that, firms are going to choose maybe the price, maybe the quantity, maybe some investment strategies in order to acquire some assets to produce, or maybe investments in research and development that maybe in the short run will imply huge costs, but in the future might lead to some innovation, and that might lead to more market power. Even more, maybe even a monopoly status thanks to a patent. Candidates in an election choosing platforms. Very simple models of game theory models of politics involve a spectrum from extreme left to extreme right, where people have their preferences and they place themselves pretty much, they don't tell it to everybody, but they are placed on this spectrum. And depending on the density of people, where people are located, candidates to some elections of some sort might decide to position themselves more or less to the right, maybe on the center. Think about, for instance, left-wing versus right-wing candidates. Some, even in the right, among the right-wing candidates, we find some extreme right-wing candidates, some moderate right-wing, and maybe some more towards the center right-wing candidates. Those positions are have been thought of. A candidate doesn't choose to be at the extreme right as opposed to moderate right just because he has a specific opinion about different matters. Some might decide to get more on towards the extreme or more towards the center because they feel that they could get more votes given the strategy of their competitors. So there is this classic game theory model where people are uniformly allocated throughout the political spectrum. You have 2 candidates, 3 candidates, 4 candidates competing with each other, and knowing the distribution of votes along the spectrum, they have to choose the optimal location. They have to choose their optimal location on the spectrum. So they have to choose the intensity of their ideas in order to win the elections. Animals fighting over prey, choosing time at which to retreat. It is not necessarily something they think about in terms of payoff matrix like we did last week, but if you observe animals in the nature, you will find that some animals wait for dusk to start hunting. Some animals live at night. That could be because during the day they might be hunted by other animals, and vice versa. bidders in an auction choosing a bid. After all, if you are competing with other bidders for a single good, everybody has to choose how much to bid, and depending on the rules, we're going to have different sets of strategies, and we're going to have different Nash equilibria. You might not be aware of this, but there are many different types of auctions. Each of them come with a set of rules that are going to imply different strategies and different Nash equilibria. Some auctions are about bidding one after the other until there is no higher bidder. Others are about the price of a good being fixed at a very high level and decreasing over time, and the first person who stops is going to be the one to buy to get the good. There are auctions where you can only submit one bid in a sealed envelope. So everybody submits one bid in a sealed envelope, and the highest bid is going to be the winner. There are some auctions where the highest bid is the winner, but the price paid is the price of the second highest bid. It is called a second price auction. Auctions are fascinating, and it is a huge topic in economics. In fact, it is a very difficult topic when you start digging into the theory, and there are many economists who develop some research, especially game theory research in auctions, so that nowadays Google and other search engines hire economists to design the best online auctions. If you don't have an ad blocker on your browser, then as you scroll down when you make a search, you will see ads pop out on the side. Those ads, every time you refresh, are going to be different ads. Those are auctions. Those are live auctions. For each click, for a certain amount of time, there's going to be an ad that's going to pop out. Economists are hired to design the best rules for advertisers to bid so that their advertisement will show up on your search. True, auction can also be more about behavioral economics, but behavioral economics doesn't only look at how an auction is organized, does not only look at how a market transaction is organized, but more generally is interested in any type of economic behavior. Behavioral economics also look at, for instance, procrastination. They make models of procrastination about why do people procrastinate? Is it about the value of time? Is it about their preferences? And so on and so forth. They try to rationalize discounting. Why do most people prefer to pay for the trip before going to the trip than after? Technically, if you think about interest compounding, you would like to delay your payments as much as possible because in the meantime you can gather interest. However, if you ask people in general, most of them prefer to pay for their trip before to have this kind of feeling of relief that they won't have to pay $1,500 after their trip. So they feel like their budget for the trip might be more like pocket money they can spend on site. And there are many other topics like that. Topics related to risk. Why do people take specific risks? It could be just straight gambling, but it could be also related to the type of pay they are going to accept once they get hired for a position. Do they want to be paid by commission 100%? Do they want to get paid fixed wage? A bit of both? Do they want to get stock options? Do they want to get maybe perks, other benefits, bonuses, and so on? So, behavioral economics is wider than just auctions. Auctions is just another market mechanism where there is one good, so the supply is equal to 1, but the demand is equal to 100 or 50 or 1,000. It depends. In this lecture, we are going to go over games where actions are continuous, such as firms competing with each other in prices or in quantities. So they have to choose quantities or prices which are continuous. This is something we haven't seen yet. So far we have seen discrete actions, discrete strategies, confess, not confess, enter, not enter, and so on and so forth. When we have continuous actions, the payoffs are not discrete. There's going to be a payoff for each quantity or each price. So it's going to be a continuous function. If you think about a consumer, it is going to be a utility function. If you think about a firm, it's going to be a profit function. Now, you already know what to do with a utility function and a profit function. One way or another, you're going to use calculus. You're going to obtain first order conditions, set the first derivative to 0, and find the optimal quantity, price, or any other variable. So when games involve continuous actions, we will have to maximize payoffs and payoff functions, and we will use calculus. The outline for this lecture is going to first to cover oligopoly. So we went over monopoly. Mono means one in Latin or Greek. I never remember. And we went over the case of perfect competition, where there are so many firms and they are so small that there is no market power. We also saw that there are some pure monopolies in real life, only a few, and they are justified by different arguments. Most of the markets we face in real life are in oligopoly. We have a couple firms. Oligo means a couple or multiple. Firms competing with each other. Because they are only a couple of firms, they have some market power, so they will have to choose the price and the quantity facing competition. And that will be modeled by non-cooperative games. In particular, I will go over competition in quantity. That is called Cournot competition. Cournot was a French guy, so that's how you pronounce it. You just don't pronounce the T. So you could say Cournot or Cournot, which is the correct way to say it. But please don't say Cournot. Then we're going to go over competition in prices, which was first modeled by another French guy. Sorry about that, guys. Called Bertrand. I know it's going to be very hard for you to pronounce. Most of you guys probably will say something like Bertrand. No problem. But again, don't pronounce the D. All those TDs at the end of French names, they are never pronounced. And then I'll go over games of collective action. This is something I already covered 2 weeks ago when I talked about public goods. This time, we will go over a model of provision of a public good where each individual will individually contribute to the provision of a public good. Thinking that somebody else is also going to contribute, we are going to see what is the optimal strategy for one individual. So we will compute the Nash equilibrium. What is the best response, your best contribution, given the contribution of the other? And you can already guess that we're going to go through the free rider problem. So let's cover oligopolies. A market is an oligopoly if it is dominated by a small number of sellers, oligopolists, who each have a non-negligible effect on prices. Oligopoly is a market form in between perfect competition and monopoly. This is the form we encounter the most in real life. We have a lot of economic models that study oligopolies. I talked about Cournot. That's going to be the first model today, where firms compete in quantities and they sell exactly the same good. So you could imagine something like the retail industry. You could think about Safeway versus Save On versus Target versus Superstore. They all sell the same things, candy bars, the same products. They don't make them. They have to choose the quantity to put on their shelves. That would be the Cournot model. The Bertrand model, who came a bit after Cournot, was a reaction to Cournot. Bertrand thought firms don't compete in quantities. They choose the price, and given the price, then the demand is going to come or not come to the store, and then the firm will produce whatever quantity is needed. So in the Bertrand model, firms will compete in prices, and they will sell a homogeneous good as well. Price competition with differentiated products. So that would be a case where goods are good substitutes for each other, but they are not exactly the same. So that would be a case where each firm has a specific demand directed towards themselves, but it will also depend on the price or the quantity set by the competitor. Typically, Coca-Cola and Pepsi-Cola. Coca-Cola faces a specific demand, Pepsi-Cola faces another specific demand, but each of these demands will also depend on the price or the quantity of their competitor. If the price of Pepsi-Cola is very, very high, the demand for Coca-Cola, the substitute, will increase. So firms have to think about the fact that they are not selling exactly the same good, but there is another good close enough that competes with theirs. Hotelling model is another model of product differentiation. It is not something I will cover in this lecture, but it is a fascinating model where the source of differentiation between the products is going to be the distance people have to travel to go to one store or the other. Both stores sell exactly the same thing, but to get to one store, it might take longer than to go to the other store. Firms will be aware of that. They will be aware of how many customers are around their area, and this might give them more or less leeway regarding the price they charge. Typically, if you are in a remote part of the world, let's say northern BC, and there is only one grocery store in town, you can allow yourself to charge very high prices because the next competitor is located 4 or 5 hours away by car. So consumers are kind of trapped. They won't travel that much just to do groceries every week. So maybe you can allow yourself to charge higher prices. And there are many, many more. Models can include also investments in research and development. They can include predatory behavior, entry to an industry, exit to an industry. All of these models can be represented in the form of a game where agents are competing with each other. They take actions, they choose strategies, and this will affect their payoffs or their profits. So let's start with Cournot. This model is named after Antoine Augustin Cournot. Don't worry about the dates. You don't need to remember them. You don't need to remember that his name was Antoine Augustin. Same, just very, very French names. Remember though that if you hear Cournot, you have to think competition in quantity. So we have two firms, and they both produce a homogeneous good. They both sell the same good. Think about stores selling candy bars. Firm I's output is going to be labeled small qi. It is bigger or equal to 0. A quantity cannot be negative. And let's assume that the firm's marginal cost is constant and is equal to C. So note that there is no I at the bottom of C. In this model, I made this very simple assumption that the marginal cost is the same for both firms. So the total industry output will be big Q equals Q1 plus Q2, the output produced by both firms. The demand function does not depend on the quantity produced by one firm in particular. It's a function of the overall quantity produced. Since the good is exactly the same, then the demand function P will be a function of big Q. And you can decompose big Q into small q1 plus small q2. So the rules of the game are as follows. Firms simultaneously choose their own output qi, taking the rival firm's output as given. So if I am firm 1, I'm just thinking, okay, the output of firm 2 will be equal to q2. I will not be able to know it. I just take it as a constant, q2. Now, if firm 2 produces an amount q2, what is the amount I want to produce? That will be my strategy, and that will be how we will find the best response of firm 1 and of firm 2. So here, the strategies are going to be the quantities. Firm I is going to maximize its own profit, pi I. Pi I will depend on qi only, because everything else is taken as a constant. So, it's going to be price times quantity, A minus B times BQ. That's the demand function, times the quantity that firm I is going to sell, minus the cost of producing a quantity qi. I added here the subscript I on the C to show you the general idea. Later on, once we plug numbers, I might set the marginal cost to the same number for both firms or a different one. Well, we have a profit function that depends on one variable. So what we can do now is take the first order condition. We take the derivative of pi I with respect to qi. We set it equal to 0. And that gives us the best response function. Why best response? Because this derivative will include qj. Qj being the quantity set by the other firm, which is going to be embedded in big Q. This will give you qi, the best response, so the best quantity firm I can set when the quantity that firm J sets is equal to qj. So again, it is a function of the other firm's strategy. It is exactly the same as in the discrete case. In the discrete case, when we went through the prisoner's dilemma, we talked about confess and not confess. And we saw that confess was the best response to confess, and it was also the best response to not confess. It is exactly the same notation as here. Confess will be the best response of firm I to the other firm choosing to confess, for instance. So again, the best response is always a function. It depends on what the other player does. Now, once you do this for firm I, you can do it for the other firm. You can do this for firm I is equal to 1, firm 1, or when I is equal to 2, it's going to be for firm 2. Once you compute both best responses, remember, you want to find the spot where both players are playing a best response to each other. This is where the Nash equilibrium will be at. So, I'm going to call it Q1 star, Q2 star, will be the Nash equilibrium if Q1 star is the best response to Q2 star, and at the same time, Q2 star is the best response to Q1 star. Okay? So let's plug some numbers. Note here that for the marginal cost, I remove the subscript I to make the math easy. So the marginal cost is the same for both firms, and that will simplify the results. If you maximize the profit of firm 1 with respect to Q1, you get that the best response of firm 1 to any quantity that firm 2 is going to decide is equal to A minus C over 2B minus 1 over 2 Q2. You see that Q2 shows up on the right hand side, and this is the only variable. A, C, and B are numbers that are given to you at the beginning of the exercise. If you do the same thing for firm 2, well, you can look at the similarity between the profit functions, and since now you take the derivative with respect to Q2 and you take Q1 as a constant, then what we're going to get is the exact same formula as before, but the notation is going to be reversed. I strongly encourage you to do this at home again, or maybe at the break quickly, just a bit of calculus. This is something you will need to know for the midterm exam and for the final exam, and maybe for future quizzes. Now, we have our two best response functions. We want to know the point where both best response functions apply or satisfied. So, if in equation 2 here, you replace Q1 by the best response of firm 1, then you are including the best response of firm 1 into the best response of firm 2. And if you replace Q1 by this expression, now the second equation here will only contain Q2. There's going to be Q2 on the right, and there is Q2 on the left. You can solve this equation and find the Nash equilibrium. It is a system of two equations, two unknowns. No more, no less. Again, I strongly encourage you to do it at home. And you should get that the quantities are going to be exactly the same. It's going to be A minus C over 3B. Here, they are exactly the same because the marginal cost is the same across firms. If firm 1 has a marginal cost of 1 and firm 2 has a marginal cost of 2, then this part here will change. It won't be just C. It will be minus 2 times your cost plus the cost of the other firm. This is something you can check on your own. You can put C1 here, C2 here, and do the whole math. Once you get the quantities, you can plug them into your profit function and see what the profits, what the payoffs are going to be at the Nash equilibrium. Again, it is going to be symmetric because the marginal costs are the same, and the profits are going to be equal to A minus C squared over 9B. Now, it is interesting to compare the case where two firms compete with the case where there's only one firm on the market, it is a monopolist. If the firm was a monopolist, the monopoly quantity using marginal revenue is equal to marginal cost would be equal to A minus C over 2B. Now, if you compare this with the overall output when two firms compete, you can add those two numbers and it will give you a higher number than QM. So the overall quantity when firms compete will be higher than in the case of a monopoly. As a consequence, you can imagine that the price under Cournot competition will be lower than under a monopoly. And the sum of the profits when firms compete is lower than the profits a monopolist would make. So too much is being produced because of your competitor, Because of that, the price is too small compared to the monopoly price. And overall, in this whole industry, as a whole, profits will be lower than if the firm was a monopolist instead. More generally, you can solve the same problem if you have more than two firms. Imagine you have n firms. N could be 10, 30, 40, and so on. Doing the math would give you Qi equals A minus C over B times n plus 1. So if you have two firms, n is equal to 2, and that would give you A minus C over 3B, the quantity found exactly here. So this is the more general formula that applies when all of the firms on the market have the same cost. If they don't have the same cost, again, this formula will be different. Once you have the quantities, you can plug all of them in the demand function to get the price. Note that the price depends on n here and n here. And finally, profit of each firm will be A minus C squared over B times n plus 1 squared, which in the case of n is equal to 2, comes down to A minus C squared over B times 2 plus 1 squared. 2 plus 1 squared is 3 squared, which is 9. And you go back to the two firms case. Any questions so far? Note that this model will be also studied in another class, ECON 325, which is called Industrial Organization. ECON 325 studies markets in particular, types of competition, monopolies, oligopolies, price, quantities competition, and so on and so forth. Here in ECON 302, we look at those market interactions as a game that we analyze through the concept of a Nash equilibrium. Let's see how it looks graphically. So, here on this graph, I'm going to report Q1 on the x-axis and Q2 on the y-axis. So I'm going to represent both firms' best responses. This line, the cyan blue line, is the best response of firm 2 to the quantity set by firm 1 in general. So this is pretty much the graph of this formula here. I am plotting best responses. Okay? So when Q1 is equal to 0, you can pretty much plug Q1 is equal to 0 here, sorry. This whole term is equal to 0, and you end up with A minus C over 2B. That's here, the vertical intercept. And analogously, when Q2 is equal to 0, you find the corresponding Q1. That gives you the best response function of firm 2 to firm 1. Now, let's also plot the best response function of firm 1. Based on the previous formula, you get the best response function of firm 1. Again, you can compute the intercepts and you obtain the following graph. Now, the point where both best response functions intersect is going to be the Nash equilibrium. Why is that? This is because at this point, the best response of firm 1 takes into account the best response of firm 2 and vice versa. This point is the only point where they both play a best response to each other. If you want to see this, well, think about firm 2. So think about the cyan blue curve. If Q1 is equal to this point here, the best response of firm 2 is going to be here. But if firm 2 chooses this quantity that you can align here, the best response of firm 1 is not to choose this number, is rather to choose this number. Now, if firm 1 chooses this quantity, firm 2's best response is not to charge this quantity, it's going to be to charge this quantity. And in fact, you can do this process at any point, and every time it's going to give you a different point. However, once you're here, if Q1 is equal to this number, the best response of firm 2 is going to be Q2C. C stands for Cournot. At the same time, if firm 2 decides to charge or to produce this quantity, the best response to firm 1 is going to be to align Q2C on the blue curve, and we get Q1C. At this point, they both play a best response to each other, and this corresponds to the number we found before, A minus C over 3B. Here, because it is symmetric, we're going to end up with the same number. But remember, if costs are different, one quantity could be lower than the other. One firm's quantity could be lower than the other firm's. So let's summarize what happens in a Cournot equilibrium, or a Cournot-Nash equilibrium, which I call here. Whoops, my bad. I always forget I am in the way. This is the same number we found in the previous slide. No, I do not provide these formulas in exam. You don't have to know them by heart. If you want to, you can, but you don't have to. I do not provide any formula in the exams. In a Cournot equilibrium, each firm's profit is decreasing in the other firm's quantity. We can see this by looking at the profit functions. The profit of firm 1 depends negatively on the quantity chosen by firm 2. So when they produce the output, firms impose a negative externality on their rival. The idea is that if firm 2 produces a certain quantity or a high quantity, it will lead to a lower overall price on the market. And because it is going to lead to an overall lower price on the market, this is going to hurt firm 1. So, in some sense, it is not really an externality because it is taken into account by the market. When firm 2 produces, the price on the market will react to that. So, careful here. The word externalities is not really correct because it is taken into account by the market. And as we saw, in equilibrium, the firms produce too much output relative to joint profit maximization. If they decided to maximize their profits together, they would act like a monopolist. They would choose the price of the monopolist. They would sell the quantity of the monopolist between both firms. So they will have to decide who is producing how much, and they would share the profits. They would share the monopoly profits. because they do not cooperate and they harm each other when they produce, they fail to maximize their joint profit. Also, because they fail to maximize joint profits, they have an incentive to collude, to cooperate. They want to talk to each other. They want to say, hey, let's stop competing with each other. Let's both decide on a common price. The monopoly price is going to maximize our profits and then share higher profits than if we compete with each other. Collusion is illegal. It can happen. It has happened many times. Many firms have been caught by antitrust competition authorities, in particular in the US and in the European Union. You can actually take a look at some of these cases online. It's pretty interesting. There was a collusion in the glass industry, glass as in car glass. There was a collusion case for the gas industry in Europe as well. There was a collusion case on the shrimp market. Big fishing firms colluded with each other to charge high prices on shrimps. And there are many other ones. Fertilizer was another one. You can find those cases online. It's pretty interesting. And the fines are big. Firms are subject to fines in the order of millions and millions of euros or dollars. If they have an incentive to cooperate, they also have an incentive to cheat on the agreement they could reach. So what's interesting is firms could call each other and say, hey, let's stop competing and let's charge a high price or a high quantity or low quantity if it's Cournot. Firms could say, yeah, sure, I'm going to produce this much, you're going to produce that much. We all agree. From tomorrow on, we are going to enjoy half of the monopolist profit each. However, each firm at home after the meeting can just think, if I know that my competitor is going to charge this price or this quantity because we agreed on it, then it is not my personal best response to charge this quantity anymore. I want to change my quantity to make even bigger profits. When firms collude, they choose the quantity based on joint profit maximization, which includes the effect they have on the other. So by maximizing joint profits, firms internalize the effect they have on each other. They decide on the quantity, the monopoly quantity, but after this, firms could unilaterally compute their best response, use the formula we found, and if you plug the monopoly quantity into the best response, you will find that the monopoly quantity is not the best response. You producing the monopoly quantity is not the best response to the other firm producing the monopoly quantity. You want to produce a different quantity that's going to maximize your profit. Now, even more interesting, what if both firms think about this at the same time? If they both think about this at the same time, they will both produce their best response thinking the other firm is going to charge the monopoly quantity. And that will lead to lower profits. They are going to harm each other. So the agreement, any other agreement than the Nash equilibrium we just saw, will not be self-enforcing. Firms will not have any personal incentive to follow the agreement. They will have an incentive to cheat. Later in the game theory chapter, we will go over a case where they do have an incentive to cooperate, but that's if they interact infinitely many times on the market. If they play this competing game every day for the rest of their life, then they might have an incentive to cooperate, thinking, shoot, if I cheat today, the other firm might be mean to me forever. And if the other firm is mean to me forever, that might mean low profits forever. As opposed to, maybe today I won't make as much profits, but I'm going to make a steady a good, steady stream of profits for the rest of my life. That's going to come later in the game theory chapter. Any questions about Cournot competition? You will go over examples in tutorials. There are many examples, numerical examples online that you can take a look at for 3, 4, 5 firms, different costs, same costs. I really recommend you to go over them, to go over the maximization of the profits, to see how to compute the best responses, to see how to get this graph, and so on. One thing I want to add, but that's really an addendum, it's really an extra. It turns out that this solution that we found here can be obtained by iterated deletion of strictly dominated strategies. So the math we did here is just, it's the equivalent of cell inspection, but with continuous actions. You could also use iterated deletion of strictly dominated strategies by starting with the first quantity and say, okay, if this firm charges this, then this firm will never charge that. Dominated. If this is dominated, then the other firm also has a dominated strategy. And if you go back and forth many times, you will end up with the same outcome, the same Nash equilibrium. Any questions? Okay, well, it's been 50 minutes, so let's take a break. I know there's a lot to handle. Let's take a break of 10 minutes. Let's resume at 12:30, and then I will talk about Bertrand competition. After going over competition in quantities, let's now turn to competition in prices. Bertrand, back then, reacted to Cournot thinking firms don't compete in quantities. They have their own store and they can choose whatever quantity they have on the shelves, but they always have some storage at the back. They always have some stocks. Rather, they choose prices. That was his intuition. They choose prices, and given the prices, they're gonna have more or less consumers coming to the store wanting to buy the product. So the quantity will just adjust to satisfy the demand given the price firms choose. Another very French name, well, from the 1800s, what would you expect? So the Bertrand model comes from Joseph, Louis, François, Bertrand. I'm thinking 2 out of those 3 first names are king's names. Yeah, that's so French. Well, yeah. So now we still have 2 firms. They sell exactly the same good. So again, think about Safeway versus Nestor's, or versus Save-On, or versus Superstore. And they produce a homogeneous good. They have to choose a price, PI, which is going to be bigger or equal to 0. And they each have a constant marginal cost, CI. Note that here I put a subscript on the cost. Let's assume that the demand is linear to make things easy. So it's going to be a linear demand, but it's going to be a piecewise linear demand. What I mean by piecewise is there's going to be a certain function, then there's going to be a kink, then the function is going to change its direction, and then there's going to be another kink, which is why we have this demand described in 3 different parts. I'm going to assume here that if a firm has the lowest price, then everybody is going to purchase from that firm. So a firm gets all the demand if the price is lower. I'm going to assume it gets half of it if it is the same. So if both firms propose the same price, I'm going to assume for simplicity that firms are going to each sell half of the overall market. In real life, in practice, this is not true at all. The price could be exactly the same between 2 stores, but it could be a random fact that some days one firm is going to sell 60% and the other 40%, and the other day could be the reverse. People go to whatever store they like. They don't choose, which store is not at 50% yet, so that they each sell half of the market, just to make things easy. And if the price is higher than the price of the other firm, then in this case, this firm will sell absolutely nothing. This gives you this demand function D, which is A minus PI, which is a linear demand, a constant minus a slope of 1 times the price. So note here that this is a direct demand, quantity as a function of the price, because since we are looking at a competition in price, we want prices to show up as the main variable. With Cournot, we wanted quantities to show as the main variable, and price was a function of the quantity. So for Cournot, we use inverse demands. For Bertrand, we use direct demands. Something to remember for the future. If PI and PJ, so if both firms' prices are equal, then firm I is going to sell to half of the market. So it will sell the overall quantity, A minus PI, divided by 2. If the price of firm I is bigger than PJ, than the price of firm J, then the demand will be 0. Nobody is going to buy from firm I. The rules of the game are as follows. Firms simultaneously choose prices, PI and PJ, taking the rival firm's price as given. So here the strategies are the PIs, not the QIs. Because they compete in prices, they have to choose a price. Now, firm I is going to maximize its payoff. Its payoff is going to depend on the price it decides, and is going to take PJ, the price of the other firm, as given. So the profit is going to be price minus cost times quantity. Here I factorize them, but you could also expand them the usual way to get total revenue minus total cost. Here there's a marginal cost which is constant, so we can put them together. But if there is a fixed cost, remember that this formula will not be valid for the profit, because we will have to include the fixed cost somehow as an extra term. Now things are a bit tricky here. I said before that actions are continuous, so in principle we should be able to use calculus. Now, the problem is calculus sometimes does not work. I don't know if you guys are aware, or maybe you've seen it in calculus classes, but some functions could admit derivatives except at some specific points. In particular, those points are kink points. If you are at a kink point in a function, the derivative is not well defined, because whether you come from the left or from the right, your answer is going to change. When your function is smooth, there is no kink, there is no angle, then you can increase by 1 unit or decrease by 1 unit. The slope of the tangent will be the same. If you have a kink, the tangent on the left will not be the same as the tangent on the right. So calculus here is not going to help us. What we can do is just use our intuition and then graph the best responses, the best response functions, see where they cross. Again, P1 star, P2 star is going to be a Nash equilibrium if P1 star is the best response to P2 star, and at the same time, P2 star happens to be the best response to P1 star. Mutual best response, this is the definition of a Nash equilibrium. So let's just go over the analysis. Let's use our intuition. By pricing just below the other firm, each firm can get the whole demand. So if my competitor charges a price of $20, I don't need to charge a price of $10. I can charge a price of $19.99 and I'm good. So firms have a strong incentive to undercut their rivals. Strong incentive to decrease the price by a tiny amount. In mathematics, we would call this tiny amount epsilon because it is arbitrarily small. In real life, we cannot go arbitrarily small. We can decrease at least by 1 cent. So if the price of the other firm is 20, you can charge 19.99. According to the model, this is enough for people to come to your store and not to the other store. So, I'm going to make a claim, which is also another way to find the Nash equilibrium. I'm going to say that in the unique Nash equilibrium, so that's a claim, it is going to be unique, both prices will be equal to the marginal cost pricing. And, well, if the price is equal to marginal cost, that should ring a bell. ECON 201, perfect competition. So that's weird. Two firms with market power here will end up charging a price equals to the marginal cost. Let's go over that. Let's think about the best response of firm 1 to the price of firm 2. First of all, if the price of firm 2 is lower than the marginal cost, firm 1 will not choose a price even lower, because in this case, it will make a loss. Any price lower than your costs and you make a negative profit. You prefer to make 0 profit to minus something. So in this case, the firm can set a price equal to the marginal cost. It doesn't matter, it is going to lose the race. Firm 2 has the lowest price. So firm 1 will not make any profits. So anything bigger than C will be a best response. Anything bigger than C. Firm 1 doesn't have any incentive to get to a price lower than C because it will make a loss. Of course, in real life, there are other considerations. Some firms might be willing to make a loss temporarily to be able to drive the competitor out of the market and then make more profits later by being a monopolist. Those are assumptions we are not making here. Now, if the price of the other firm is between the marginal cost and PM, which is the monopoly price, then firm 1 wants to undercut the price of firm 2 by a tiny amount. In mathematics, we represent this tiny amount by the letter epsilon. So here epsilon is not an elasticity, it is an arbitrarily small amount. It could be 0.000000001. Doesn't matter. Or it could be 1 cent, the smallest possible number you can find. Why do I say that P2 should be lower than PM as well? Because if the price of firm 2 is bigger than PM, than the monopoly price, firm 1 doesn't want to charge a price slightly lower because PM is going to maximize the monopolist profit. If firm 1 charges a lower price, it will be a monopolist. So in this case, it will rather charge a price equal to the monopoly price. Right? Now, finally, the last case. If the price of firm 2 is bigger than PM, then, that's what I said, firm 1 should choose a price equal to PM. And this gives us the range of best responses for firm 1. When P2 is lower than C, I choose C. When P2 is between C and PM, I should choose just slightly lower than P2. Finally, if P2 is strictly bigger than PM, I maximize my profit by applying monopoly pricing. Again, you can see that I have 3 different pieces here. So my demand will not be smooth. It won't be just one straight line. They are going to be kinks. I can make the same analysis for firm 2. I can pretty much replace P2 by P1 and I am set. I get the best response of firm 2 as well. Interestingly, those best responses will only intersect when the price is equal to the marginal cost. This is hard to see mathematically because of this piecewise best response, but graphically it will be obvious and the intuition is kind of straightforward. Imagine that your competitor chooses a price of 20. You want to set a price of 19.99. But then the other firm is like, well, if I charge a price of 20, this guy is going to charge 19.99. So I should charge 19.98. And then you're going to think, wait a minute. The competitor is going to anticipate I am going to charge 19.99, so he's going to charge 19.98. If he charges 19.98, I should charge 19.97. And then the other firm is going to think the same thing. He's going to say, yeah, well, this guy is going to go 2 steps ahead. He's going to anticipate I'm going to charge 19.98, so he's going to charge 19.97, so I should charge 19.96. And by reasoning this way, we're not even talking to each other. It's just, I'm just thinking about what the other firm is going to do, given the rules of the game. I want to go lower, but the other firm also knows that. So the other firm is going to go lower. So I'm going to have to go even lower, and even lower, and even lower. And so mentally, the process is going to be undercutting each other's firm until when? Until they reach their marginal cost. Once they reach their marginal cost, they do not want to go lower. If they go lower, they will make zero profit. So once they are at the marginal cost, they're like, I'm done. I don't want to go any lower. If I go lower, it's going to be negative. Right now, I might make at most zero profit. But by zero profit, remember, we mean I can pay my employees, I can produce the good, I can make a living. If I start making a loss, it means I don't have enough money to pay my costs. And that's going to be a problem. So the reasoning is, I know that you know, that I know, that you know, infinitely many times until you get to your limit. The limit is going to be dictated by the marginal cost. This is what we call common knowledge of rationality. I know that you know that I know that you know. This is the knowledge that my opponent is rational. And this is my opponent's knowledge that I am rational. If we all assume and know that we are rational, we are both going to do this thought process in our head, and we are both going to reach the same conclusion: price equals marginal cost. It's interesting, because this means that if firms compete in prices, you only need two firms, and it's as if they were in perfect competition. It's a very powerful insight. Let's look at the graph. Whoops, I see a question first. When P2 sets the price over PM, why can't P1 set the price right below the P2, such as P2 minus epsilon? Because P2 minus epsilon will not maximize the price at this stage. If the firm is alone on the market, the monopoly price is going to be the profit maximizing price. We saw that a couple weeks ago in the monopoly lecture. Remember that if the price is too high, a firm will not sell anything. So a monopolist doesn't want to charge too high of a price. The price is going to be high, yes, but it won't be too high. Apple doesn't want to charge $1 billion for an iPhone, because by decreasing the price to $1,000 or $800, they're going to sell millions of units and they're going to have higher profits. So if a firm is alone on the market, the monopoly price is the profit maximizing per unit price, excluding price discrimination, of course. So if firm 2 decides a price which is higher than the monopoly price, going slightly lower is like charging $1 billion or $999,999,999 for an iPhone and 99 cents. This is so hard to say. I tried. Okay? Rather, it will go to the monopoly price and say, hey, monopoly price is the best. It will be a monopolist and it will maximize its profits. Okay. Let's look at the graph. So instead of representing Q1 and Q2 like I did with Cournot, this time I'm going to represent P1 and P2, the best responses. Let's look at the best response of firm 2. P2 as a function of P1. First thing is, when firm 1 charges a price which is lower or equal to C, so this range, firm 2 doesn't want to undercut firm 1. Firm 2 wants to charge a price equal to the marginal cost. So the best response will be flat, marginal cost, all the way. Because any price lower will not do. Now, as soon as the price of firm 1 gets bigger than the marginal cost, then we are entering in the phase where firm 2 wants to propose a price slightly lower. And here, I represent the slightly lower with my function being slightly lower than the 45-degree line. This is on purpose. Those lines are not overlapping. The 45-degree line is the line where P2 is equal to P1, Y is equal to X. Firm 2 wants to charge a price which is slightly lower. And the tiny difference here between the blue line and the 45-degree line is going to be my epsilon, my 1 cent difference. Finally, once firm 1 charges a price equal to PM, which is here at this kink, or anything above, firm 2 wants to charge the monopoly price. Firm 2 will be the only one to sell. Being a monopolist, if it can charge the monopoly price, it will. And this is how you end up with this best response function, which is all kinky. Okay? Now, let's do the same thing for firm 1. So we have to do the reverse. It's kind of less intuitive to do the reverse, but let's go over it. When firm 2 charges a price between 0 and the marginal cost, anything here, firm 1 wants to charge exactly the marginal cost. So that's why it is vertical here. Once they get there, any price P2 which is bigger than C and lower than PM, so anything here in between, and firm 1 will want to charge the price P2 minus a tiny epsilon. So in this case, you're going to go to the left. Boop. The epsilon is going to be just slightly point to the left. This is the phase where firm 1 wants to undercut firm 2. Finally, once the price of firm 2 is bigger than PM, then firm 1 wants to stop at PM because this is where firm 1 will maximize its profits. Note that here they do not cross. Both best response functions are on either side of the 45-degree line. The only spot where they meet is going to be here. And this goes back to the intuition I gave. I know that you know that I know that you know. So we undercut each other mentally and we end up both at the marginal cost. Any questions? You are expected to know how to graph this. So make sure you can walk through the process again and you know how to graph these best response functions. Bertrand competition takes less calculus. In fact, it takes no calculus, but it takes a fair bit of intuition and some graphing skills to see where the Nash equilibrium is going to be. In the chapter about game theory, so we have 3 more lectures about game theory. There are going to be graphs, similar graphs like this, where we plot best response functions and we see where they meet. Those are graphs you will be required to know for the exams and the quizzes. No questions? Okay. So let's summarize. The same way we summarize Cournot, let's summarize Bertrand. In a Bertrand oligopoly, each firm's profit is increasing in the other firm's price. This is the opposite of what we saw with Cournot. Each firm's profit was decreasing in the other firm's strategy, the quantity. Now, if the other firm charges a high price, your profit is going to increase as well. You just charge a cent less, but you can charge a higher price because the competitor is charging a high price. So in raising their price, firms now impose positive externalities on rivals. Again, externalities here is quotation marks because the price, the change in the price, the increase in the price will be directly reflected on the market through a change in the quantities. By raising the price, yes, the quantity sold will be lower, but if you charge 1 cent lower than your competitor, you will still sell all of that quantity. In equilibrium, the firms set the price too low relative to joint profit maximization. In fact, price is equal to marginal cost. It is way lower than the monopoly price. And the other thing is, two firms are enough to generate marginal cost pricing, to generate the competitive equilibrium, which is efficient. And this is what we call the Bertrand paradox. It's a paradox because we have competition, but we have limited competition because firms have market power. We have an oligopoly, yet the outcome is as if there were 1 million firms on the market, all too small to influence the price. This is what the paradox says. If competition is in prices, two firms are enough to lead to the competitive outcome. And that's the end of the day. You're good. You don't have to be worried about, oh, it's only two firms, it's very close to monopoly, and so on. If they compete in prices, you can leave this market alone. It is the competitive outcome, Pareto efficient. Now, you can imagine that in real life, those assumptions, some of these assumptions just do not hold. And I will get into this in a slide. First, I want to compare Bertrand and Cournot. Both models are similar in the sense that the equilibrium price will be lower than the monopoly price. In the Bertrand case, the equilibrium price will be way lower. But in the Cournot case, it is also lower than the monopoly price. In both cases, firms fail to maximize their joint profit, so they fail to maximize the monopoly profit. They have incentives to talk to each other, cooperate, or to collude. Again, collusion is not sustainable though, because they have an incentive to promise, to commit to a certain price or a certain quantity, and then they have an incentive to backstab their competitor to increase their profits. Again, any agreement other than a Nash equilibrium is not self-enforcing. If you agree on anything else, your best response is not what you agree on. Your personal best response is going to be something else. The agreement, the quantity or the price to agree on, comes from maximizing two profits together, the sum of profits. Because each firm is affecting the profit of the other, when you maximize joint profits, you are internalizing the effect that your strategy has on your competitor. But if it's only about your personal profit, you only maximize your profit, you do not care about the impact you have on your competitor, and then your best response will be different from what was agreed upon. Now, there are differences with Cournot as well. I talked about the Bertrand paradox. I just said Bertrand. The Bertrand paradox. Because under Cournot, the outcome is not Pareto efficient. We don't have marginal cost pricing. Firms compete, they make positive profits, total surplus is not maximized. In the case of Bertrand competition, the paradox tells you that we are in the perfectly competitive case, outcome is Pareto efficient, we are good to go. Now, this paradox can be solved in many different ways in real life. And I will go over some of the assumptions I talked about and challenge each of them. First of all, I talked about homogeneous goods. In practice, each firm produces its own good, so products are differentiated. Pepsi-Cola versus Coca-Cola. So there's going to be a demand for each good, not one single demand. That can depend on the price of the substitute as well, which depends on the price of the competitor's good. Because we're going to have two demands now, firms will have an incentive to maybe charge a high price, but not too high. For instance, I believe, but I'm not sure, I heard way more people talk about a strong preference for Coca-Cola over Pepsi-Cola. So it seems that people who have no preferences, they don't care between Pepsi-Cola and Coca-Cola. They go for the cheapest. Okay, doesn't matter. My case, for instance, I don't really care. To me, same. I just don't have the taste buds to feel the difference. But the ones who can tell the difference, I've seen in majority, are in favor of Coca-Cola. Say, in majority of the people I know. So that's not a lot. This means that the demand is more inelastic for Coca-Cola. So Coca-Cola can charge a higher price and will not lose too many customers. Pepsi-Cola cannot afford to do that because they don't have such a big fan base. My point being that then there's going to be interactions and the final equilibrium prices will not be equal to the marginal cost. Firms will make profits and so on. In fact, if you think about, instead of talking about Coca-Cola versus Pepsi-Cola, think about Coca-Cola from Safeway and Coca-Cola from Save-On or Superstore. Both of these products are Coca-Cola, but they are still differentiated because one is sold in one place, the other in another place. If you live exactly between the two stores, it takes the same amount of time to get to the cashier. It takes the same amount of time to pay and to select your product. Then for you, the good might be homogeneous. You just go to the place where it is the cheapest. But if you live closer to a Safeway than from a superstore, then you might prefer to go to Safeway because it's closer, even if the price will be higher. And in this sense, products are differentiated as well. For you, they are different. One of them takes one bus to go to, one bus 30 minutes and so on. The other one takes a 5 minutes walk. If you quickly want to get a bottle of Coca-Cola, you will just go to the local store, even though it might be 30 cents more expensive. So in real life, the hypothesis of homogeneous goods is never really satisfied, although in the retail sector, it is close. If Safeway was right next to Save-On or Superstore, like right next to it, if there was no line when you want to pay, if it was as easy or as fast to get your product with each store, then maybe goods would be homogeneous. And then if you only need Coca-Cola, you would go for the cheapest place. I assumed as well here that if the price of one firm is lower than the price of the other firm, that firm will absorb all of the demand. Everybody is going to come to that firm's store. This is the assumption that there are no capacity constraints. Well, in reality, a firm is not able to cover the whole demand. Very often, you might show up at the store and not find a product anymore. You might have to wait a couple days for the employees to restock. If there are capacity constraints, if one firm cannot absorb all of the demand, then it means there is room for the other firm, even though the price is higher. In fact, the interesting part about this is, well, imagine everybody buys from Superstore because it's cheaper, and Superstore is sold out of Coca-Cola bottles. Then anybody who wants Coca-Cola now can only go to Safeway. If Safeway knows this, Safeway is thinking, I'm the sole provider of Coca-Cola in town. I am a monopolist now. So now I can charge a higher price, even though I will sell a lower quantity. So interestingly, in a case like that, Superstore will be sold out and they will make money, that's great. But after that, what we call the residual demand, whoever is left that could not get a bottle at Superstore, will be willing to pay a higher price at another store because that other store will be the only supplier of the good. And you can start making kind of games when you think about capacity constraints. If firms are taking this into account, then the whole game is going to change and is going to become more complex. I also mentioned that it is a one-shot model. If firms compete every day, because this is what happens in real life, the equilibrium will change. In particular, cooperation or collusion might be sustainable. And that's something I will cover in 2 lectures. If firms compete, but they compete over time forever, and the forever is important, as opposed to for a limited amount of time, of periods. If they compete forever, it is possible for them to agree on a high price and never fail on their agreement. They will have an incentive to stick to the agreement. It's a very powerful result. If you play, or if 2 firms compete with each other for a limited amount of time, let's say 6 months or something, I don't know, every day for 6 months, then they will not have an incentive to cooperate, and collusion will not be sustainable. The last assumption I made was that firms are symmetric in their costs. If firms have different costs, different marginal costs, then the equilibrium price is not equal to the lowest marginal cost. I'll let you think about it. But imagine that one firm has a cost of 10, marginal cost of 10. The other firm has a marginal cost of 5. Think about the undercutting process. They each undercut each other by 1 cent. Until what? Well, at some point you're going to reach 10, which is the cost of the first firm. That firm cannot go lower. The other firm, who has a marginal cost of 5, can go lower. So the final price will not be equal to 5. It will be bigger. And then there is going to be some profits. Profits won't be 0. Firms will make some profits, and the outcome will not be Pareto efficient anymore. So those 4 assumptions are crucial. As soon as you challenge one of them, the whole game has a new solution and new implications. I showed you the simplest, the most basic version of the game. And since Bertrand in the 1800s, many researchers have included new assumptions, like they challenge homogeneous goods, they challenge capacity constraints, they challenge one-shot models, symmetric firms. And for each of these assumptions, I gave you a rough idea of how the equilibrium will change. And each of those equilibria is more realistic than the plain Bertrand Nash equilibrium. Any questions? Okay, I don't see any question here. So, why do you say we take another break? It's been 45 minutes more or less. So, I'd say that probably your attention span is reduced. Let's take another 10 minutes break and I will move on to games of collective actions. Okay? So let's meet again at 1:30. Let's take a 14 minutes break. Okay? See you soon. Let's get back to it. After studying two different types of interactions on the market, now we're going to go over games of collective action. So firms do not have to be involved in such games anymore. That will actually, in fact, involve customers, consumers more than firms. Games of collective action are situations where the benefit to the group depends on the actions or efforts of all members. Last week, if you remember, I talked about a common project of two students where students could either goof off or work hard. That was a game of collective action. The efforts of one was had an impact on the payoffs of the other. In collective action games, individuals have a tendency to free ride on the contribution of others. They contribute nothing or too little themselves, but still reap the benefits. Contributing to a public good is the primary example. In general, this free rider problem means that there are too few volunteers, in the sense that contributions are too low, or the amount of people who agree to contribute is too low. So overall, there will be a too little group effort. Only a couple of individuals will contribute. So at the group level, effort will be too low. And the benefit from the collective action will be too low. Too low in the sense that it will not be Pareto efficient. So we will get to Pareto inefficient outcomes and market failure. One of the reasons why private provision of public goods lead to a market failure. As the group becomes larger, you can expect this problem to get worse. Detection is harder. If you are one among 5 people, people will see if you are not doing your part. If you're one among 100 or one among 1,000, you can hide behind the mass. This is kind of the mass effect. Let's go through an example. In fact, this is an example we covered in the Externalities and Public Goods lecture. Rosia and Tom moved in together and they decided to buy kitchenware they can both use. So the kitchenware was the public good, denoted by big G. They also had their own consumption of another good. It could be any other private consumption. They had an income IR and IT, respectively, for Rosia and Tom. And the utility functions were given by ln of xr plus ln of big G for Rosia. And for Tom, it would be a Cobb-Douglas utility function, square root of xt times square root of big G. The per unit price of x was 1 and the per unit price of big G, the public good, was PG. We already went over the efficient amount of kitchenware to purchase, the efficient amount G star. Using Samuelson rule, we added both marginal rates of substitution. We could also replace each private consumption of the private good XR and XT by a function of big G. And finally, we found that the optimal amount to provide was equal to the sum of both of their incomes divided by 2 times the price of 1 unit of kitchenware. I will refer you to this lecture to see how to compute it. Now, this Samuelson rule tells us what is efficient, but doesn't tell us how we're going to get there. It doesn't tell us in real life how things are going to happen, what kind of rule both Rosia and Tom will agree upon to purchase the kitchenware. What happens if contributions are individual? Imagine that the rule is, here is a pot or a box. By tonight, we are going to put some cash into the box, and then we're going to use all the cash in the box to purchase the kitchenware. Something like that. So, they are going to take into account the fact that the other is going to contribute, and they're going to have to decide what themselves to contribute. So the answer depends on how much each expects the other to contribute. It is a strategic game. If I know that whoever else I'm participating to the project with is going to chip in $500 or $1,000 or something, then I can think, well, why would this is enough. We can get enough public good with that. Why would I contribute? And then I can actually, in fact, free ride. Problem is, what if the other player thinks the same way? Well, if everybody thinks this way, then you get to the free rider problem. Everybody is going to contribute less, expecting the others to contribute. And at the end of the day, the sum of the contributions will be inefficient. We're going to solve this problem using the Nash equilibrium concept. Since we are looking at individual contributions, we are going to separately maximize utilities subject to their respective budget constraints, the same way we maximized individual profits for the Cournot model and for the Bertrand model. Let's start with Rosia. If Rosia expects Tom to contribute an amount GT to the public good, T for Tom, G for public good, her optimal contribution is going to maximize her utility. Her utility is log of XR plus log of G, subject to, and we're going to have a couple of constraints to take into account. The first one is that Rosia is going to take GT as a constant, the same way firm 1 took the quantity of firm 2 or the price of firm 2 as a constant in the two previous models. The second constraint is kind of obvious, but it is that the contribution should be positive or zero. It cannot be negative. Maybe we can model this in the form of some sort of a debt and say, I'm not paying today, but next week I'll pay you back or something. No need for that here. Finally, the budget constraint has to be satisfied. The price of the private good is equal to 1. So 1 times XR plus the amount of money GR contributed to the public good must be equal to Rosia's income IR. Note that here, on the left and on the right, I am looking at dollars. The budget constraint always represents money. Yes, there is one more constraint, is that, remember, the amount of public good that can be purchased will be equal to the sum of the contributions divided by the price of 1 unit of the public good. So that makes many constraints, but the first one and the second one are just here to reestablish the rules. The third one is the important one, the budget constraint, which we need to include in the utility function one way or another. And the last one is one we can use at the very end to see how much public good will be produced. Note that the utility of Rosia depends on big G, not on small g. It depends on overall how much kitchenware is being produced. So you can use the last constraint and plug it into the utility function to see the utility of Rosia as a function of her contribution and Tom's contribution. It is very close to a ECON 201 problem. There is one more constraint, 3 more, but 2 of them are not very important, and the last one is just there to is not a big deal, let's say. So what I'm going to do is I'm going to get rid of this XR by using the third constraint, the budget constraint. With the budget constraint, I can compute XR is equal to IR minus GR, just by putting GR on the other side of the constraint. If XR is equal to this, then I can replace my XR here by this formula, and then I can get rid of XR in the utility function, so that the utility function depends only on GR. Because at the end of the day, for this exercise, I do not care about the value of XR, I do not care about the optimal amount of private consumption, I care about the optimal amount of the public good contribution. Once you have it, you can plug this number in the budget constraint and recover XR if you want to. And if I replace big G by its function of the contributions, then my utility function becomes ln of IR minus GR, which is XR, plus ln of big G, and big G is this number. The sum of the contributions divided by the price of 1 unit of kitchenware. Now, I got rid of 2 constraints. By plugging those 2 constraints into my utility function, I am taking them into account. So once I take my first order conditions, it will automatically satisfy the constraints. So I don't need to have them on the side or think about them anymore. I need to think about the first 2 constraints now, so I just rewrite them. But again, just make sure it's positive or 0. It could be 0, pure free writing. I don't give a single dime because other people are going to contribute for me. That could be the case. Now I can take my first order conditions. Note that now the utility function only depends on GR, so I need to take 1 first order condition. The first order condition is such that the derivative with respect to GR is equal to 0, but it is not equal to 0 at any point GR. It is equal to 0 at the best response, because the best response is what maximizes the utility of Rosia. Just play with the math. By now, I think you should know your calculus rules on logarithms. If not, make sure you do for the next tests, quizzes, midterm and final. And I can isolate for GR to get the number IR minus GT over 2. So GR is the best response of Rosia is a function of how much Tom contributes. And note that since the contribution must be positive or 0, in the case where Tom contributes more than IR, the income of Rosia, then Rosia is going to provide 0. Enough public good will be purchased with Tom's contribution alone. Again, it is piecewise. So when it's piecewise, you might expect some corner solutions. Don't worry, we are not going to go through corner solutions here. This is only a technical detail. We don't really care about this in this class. Once I have the best response of Rosia, I can do the exact same with Tom. So Tom is going to expect Rosia to contribute GR and is going to maximize his utility function, which is made of square roots, subject to the same constraints, but make sure you swap the notation for the budget constraint. I do the same trick. I replace xt by IT minus GT. The last constraint as well, I plug the last constraint into my big G here. And my utility function, Tom's utility function, now only depends on his own contribution. And the contribution of Rosia is taken as a constant. Now, I do the exact same process. I have one first order condition to take. Let's go. I suggest you to do it at home. It's kind of messy because we are dealing with square roots, so I really encourage you to try to do it thoroughly. It's always good practice. And interestingly, we get a similar best response as Rosia, but the notation is now swapped. The best response of Tom, will be his income minus the contribution of Rosia divided by 2 if the contribution of Rosia does not go beyond his income. If she contributes more than his income, because the contribution must be positive or 0, then instead of being negative, Tom will contribute 0. Enough was contributed by Rosia alone, so Tom doesn't need to contribute anything. Now, we have our two best responses. It is time to solve for the Nash equilibrium. The Nash equilibrium profile, GRNE, GTNE, simultaneously satisfies equations 1 and 2. This one here is equation 2. And this one here is equation 1. So both best responses are satisfied at the same time. It's a system of equations, two unknowns. I talked about Cournot solutions. I'm going to assume that both contributions are positive. In fact, I know they will be because I chose the numbers. And if you solve this system of equations, you get the optimal contribution of Rosia is 2 times her income minus the income of Tom, divided by 3. And for Tom, it's 2 times his income minus Rosia's income, divided by 3. Note that the Nash equilibrium never depends on the other person's contribution. It depends on fixed number, exogenous variables. IT and IR are numbers which are given to you at the beginning of the exercise. When I look at best responses, I get one variable as a function of the other. Here, this is a number. This is an actual number. To put things in perspective, let's actually define some numbers. Imagine that Rosia's income is 18 and Tom's income is 15. The price of 1 unit of kitchenware is equal to $2. You can plug your numbers here into the Nash equilibrium values, and you get that Rosia's contribution is going to be 7. Tom's contribution is going to be 4. And finally, the Nash equilibrium amount of public good, using my formula from before, will be 7 plus 4 divided by PG, which is equal to 2. So 7 plus 4 is 11, divided by 2, 5.5. So 5.5 units, whatever that means, of the public good will be purchased. This is a quantity. Now, do you remember what the efficient amount of public good was? The efficient amount, using the formula from before, was G star equals IR plus IT, so 18 plus 15, divided by 2 times PG, so divided by 4. That number is equal to 8.25. And this number, the efficient amount of public good to provide, is bigger than the Nash equilibrium amount. This is free riding. If they had taken into account the effect they have on the other with their contribution, they would have contributed more. Because they do not, they only care about themselves, they decide to contribute less, and the Nash equilibrium is inefficient. If they individually contribute, they do not internalize the externality they impose on each other. And again, it's all about, do I satisfy only my own utility like a selfish, rational consumer? Or do I take into account my the effects I have on other people in my optimization problem? Any questions? The budget constraint, where does PG go? Okay, I see where your problem is. So, the budget constraint is here. The budget constraint is expressed in monetary terms. So, I define GT as money. It's money you put on the in the pot. Big G is a quantity. It is the amount of public good that can be purchased when the price is P. So, if you look at here Tom's budget constraint, his budget constraint is the price of X, which is 1 times X. That's how much money he's going to spend in X, plus how much money he gives to the public good for the contribution of the public good, equals to his income. So he's not the one buying PG times BG. PG times big G. Is only chipping in with some money. Then they add the money coming from Russia, and then they compute big G by dividing by the price. They go to the store with this money, and the number of units they can buy is equal to those contributions divided by the price of the public good. So in this example, I define contribution as money, not as a good. I could give you another example, however. I could say something like, imagine you have a potluck with your roommate, and each of you has to buy some food, but the food is going to be publicly shared. It's going to be a public good. So you buy your own beverage, but the food you buy is going to be eaten by you and your roommate, or more people. In this case, what I call a contribution could be, the amount of food you purchase. So that would be price of the food times the amount of food you buy. Here, I'm talking about a direct contribution to the public good, which is why we only see GT. So when you read problems like this, make sure you know what unit each variable is expressed in. X is a quantity, 1, 2, 3, 4. G is an amount of money, so it's $1, $2, $3. And IT is money as well, it's income. A budget constraint always has money on the left and money on the right. So make sure that when you write down a budget constraint, you are able to you make sure that you have the same unit on the left and the same unit on the right. Yeah, does it work? So just pay attention to that. It really depends on the way the problem is framed. The budget constraint is something you're going to have to make yourself every time. So think about it. It's not always P1x1 plus P2x2 is equal to income. That's the ECON 201 budget constraint. Economic problems are very different from each other, and the budget constraint can vary a lot. Any other questions? Okay, well, let's look at it on a graph. Here, I represented the best responses of Rosia and Tom. They can look like the Cournot equilibrium, but there is a tiny difference. If you remember the best response was piecewise. There was a 0 as well. Here, I need to represent that piece. So every time you have a piece, you have a kink. Let's look at the best response of Rosia, for instance. This is the dark blue line. We said that her contribution is positive. It was equal to IR minus GT. Oops, I made a mistake with the labels here. But Rosia is in dark blue. I'll change that later. So, her contribution is IR minus GT, or 0 divided by 2, or 0 if the contribution of Tom goes beyond her own income. And you can see here that when GT is beyond IR, then the contribution GR, the best response, is to contribute exactly 0, which is why here the rest of the line is in blue. It is part of the best response function. If I do the same with Tom, his contribution is positive, so all those numbers are positive, until the contribution of Rosia is higher than Tom's income. Once the contribution GR is higher, then Tom stops contributing and he contributes 0. The best responses only meet here at one spot. It is an interior solution because the math works out pretty well. And they both end up contributing a positive amount, but you can see that Tom, I have to change this notation, comes from the Cournot model. Tom's contribution will be smaller, it was equal to 4, than Rosia's contribution, which was equal to 7. Okay? Note that if the numbers were different, let's say that the numbers were such that this blue line was steeper, something like here. If it was steeper, then it would cross Tom's best response, the cyan blue line, up there at the intercept. And that would mean that this is a case where Tom doesn't contribute anything and Rosia contributes more than Tom's income. That would be a Cournot solution. So the first bullet point is supposed to be Tom's. Here, the cyan here is Tom's. So what's on the graph is correct. When the contribution of Rosia is bigger than Tom's income, he contributes 0. So the cyan blue should be Tom. It is in cyan blue, but I put the wrong notation here. I have to invert that. I will correct all those slides. I correct them every time, and I will post them sometime this afternoon or this evening. Okay? Sorry about that. Sometimes things can be a bit confusing. And let me know, by the way, if you have any feedback about the slides. If you think they are too long, too big, or not detailed enough, I can make more. I can make more slides in between to explain the graphs and so on. I appreciate any feedback, the good feedback as well as the bad feedback. Okay? The point is that you can see that the contribution of Tom here is smaller than the contribution of Rosia. So the graph is correct. I have to change notation here a bit. The efficient amount of public good was equal to 8.25. Well, 8.25 is the amount overall, but it doesn't tell who contributes how much. Is it half-half? Is it 1/3, 2/3? After all, they don't have the same income. So maybe since they moved in together, I'm just making up a story here, but since they moved in together, maybe the less wealthy one is going to contribute less. I do not know what kind of rule they set up. So the Nash equilibrium amount of public good is 5.5. The efficient one is 8.25. Now, how would we get to this 8.25? Is it half-half? What kind of rule is there? That's for another question. That would be another assumption to make, something I could ask, like in assignment 1, for instance. But it's not the point of the class here. The point of the class here is to show that the Nash equilibrium, coming from individual optimization problems, is not efficient. It is not efficient because players do not take into account the effect of their decision on the other player. They don't internalize this externality, and they end up contributing too little. So, in the private provision of a public good, there are combinations, GR, GT, that will make both better off. So the Nash equilibrium is not Pareto efficient from a collective point of view. That's pretty much what I said. An amount equal to G star, 825, is what is Pareto efficient. From here, from this Nash equilibrium, there is an allocation which makes both better off. The allocation where G star is equal to 8.25. However, the rules of the game are that they contribute individually. They do not think about the other, and this is how they end up stuck in this Nash equilibrium that is not Pareto efficient. That sounds a bit like the prisoner's dilemma, right? It is not exactly the same context, but the conclusion has the same flavor. So the idea is that each person's utility is increasing in the other person's contribution. Tom is happier if Rosia contributes more, and vice versa. There is an externality which is not internalized. However, each person's optimal contribution is decreasing in the other person's contribution. If Rosia contributes a lot, Tom wants to contribute less, and vice versa. So, they benefit from other contributions, and the more other people contribute, the less they want to contribute. And this is the free riding behavior. At the end of the day, in equilibrium, and here I mean the Nash equilibrium, people contribute too little relative to the joint surplus maximization. So, individual contribution rule is probably not, well, it's just not the best rule. Another rule could be, let's maximize our utilities together. We'll find the Samuelson rule, 8.25 for G star, and then we'll figure out how we split the costs. But that will be efficient. There are other instances where similar problems occur. The tragedy of the commons is a very famous problem. It was actually pointed out by the first female economist who got the Nobel Prize in economics, I believe. That consists in overusing common resources. Common resources such as lakes, fields, parks, and so on tend to be overused overall. The idea is that when one individual wants to use it, is not going to think about what other people, about how much other people can use it. if you decide to go to a local lake and fish, you might not think about the impact of your fishing on everybody else's fishing. By doing this, you're going to overfish. And if everybody does it this way, at the end of the day, there will be a depletion of the fish. There won't be enough fish to renew themselves on the lake. And the outcome will be inefficient. In cases like that, there have been different solutions, such as you pay to access the lake. If you pay, you are going to be, at least you are compensating you're compensating your use of the lake, and that money can be used to maybe restore the lake later. Imagine another example. You are a small town mayor in the countryside, and you have a big field of grass that belongs to the city, but nothing can be built on it. It could be some sort of a swamp, so the foundations cannot be solid. You might decide to open the field to farmers. Farmers can bring their cattle, they can bring their sheep to graze for free. Farmers might not take into account the impact of their sheep and their cows on other farmers' use of the grass. They might bring too many sheep, and if everybody does this, you're going to have an abundance of sheep and cows on the field, in fact, too many, and the land will be overused. And this is the case for public infrastructure in general, road, park. Remember that every time you go on the road, you are making a road less and less non-rival. You're making it rival. And in fact, you can make it excludable eventually because of traffic congestion. And this is the same for natural resources. Everybody who uses some natural resource for their own use might end up overusing it compared to what would maximize everybody's utility, everybody's joint utility. A note here is that other games of collective action need not share the same problems. It's not always about free riding. Okay? For instance, adopting a common standard between firms or between two people who collaborate might not be just about free riding. Or not, in fact, it will not be about free riding. Sorry. So let's finish this lecture with how to solve those problems. Free riding and other problems in games of collective action can often be mitigated or solved by, well, detection, punishment, rewards. And remember that the less people there are for the provision to a public good, the easier it is to detect the ones who don't contribute. So the easier it is to detect the free riders, and the easier it is to punish them. Or, on the other hand, to reward the ones who are contributing more. You could set a rule that says the more you contribute, maybe the more you can use a common resource. Think about the kitchenware. Imagine that Tom and Rosia can use the kitchenware, but sometimes, Tom needs all of the kitchenware to cook, and so it prevents Rosia from using it. There could be a rule that says if you contributed more for the kitchenware, you can use it most of the time, or more of the time. Or there could be something as silly as you don't need to clean it because you gave more for it. And so other people will have to clean it. I don't know. You can make up rules. The idea is that you can set up a set of rules to punish bad behaviors, low contributions, or reward high contributions. Sometimes you don't even need rules. Customs and social norms, especially in repeated interactions, will do the work for you. People pointing at you and giving you the shame look might be enough for you to contribute the same as everybody else. Being with the fear of being judged, you might just contribute your share just enough so that nobody will judge you. It's like, no, I did my share. Don't put that on me. Many societies are in fact working this way. I was thinking about a TV show that I watched recently called The Handmaid's Tale. Is it what it's called? I think it's on Crave or HBO or something. More generally, and not just this TV show, cults work a lot on customs, social norms, and the fact that people observe each other. By observing each other, they monitor each other to stay in line and follow the rules. If you live in the fear that somebody is going to report you and you're going to get punished, then you're going to stay in line and do what you're told. It is a very strong way to manipulate behaviors. Or simply it could be government provision. The government says, if you guys contribute on your own, there's going to be free riding or other problems. In general, lower contributions. It's not efficient. We'll do it for you. We are going to collect taxes and we are going to purchase the efficient amount of public goods for you. Or it could be government regulation through taxes, through subsidies. If you remember, I talked about this in the externality problem. Public goods, after all, are an example or a special case of externalities. So, Pigovian tax and a Pigovian tax or a Pigovian subsidy could give the proper incentives. We also talked about bargaining. Direct communication and bargaining could be a way to reach the efficient solution as per the Coase theorem. That's it for this lecture on games applications. We will see many more games applications from now on. These ones were particularly important because they cover a wide range of problems. So many of the problems we're going to see from now on are kind of special cases of those general problems. Have a good rest of your week and see you in the next one. Bye.